I hope you're really excited because we're entering the last part of the semester, the last part of the class. We talked about electro, right? And we learned the governor equation of electricity. We learned Gauss's law, which state how electric field behave in space. And then we learned Faraday's law. But we realized Faraday's law was not enough. It was not complete. It was not always valid. We need to have magnetism. When we apply Gauss's law on magnetism, we get 0, okay? And we see that actually Faraday's law gets updated version, right? And we saw this. And we also see that if we do not the area integral on the magnetic field, but the loop integral, right? So we actually getting this term, which you saw in the lecture, right? Is the parallel idea of how to find the magnetic fields. And this is actually all the important equation, this and also the force equation, right? Coulomb's law, the force. These 5 equations actually tell us everything we need to know about electromagnetism. And then you're gonna say, okay, I finished the class. I know electro, I know magnetism, that's all. But then come one guy named Maxwell. And he said, let's try to take these equations and push them, these 4 equations, to only 2 equations. Let's try to do it, okay? And he did that, and then he discovers something crazy. Okay, he discovers that the 2 equations are identical equations, one for the electric field, one for the magnetic field, and this equation maybe is not familiar to you, but this is the wave equation. Okay, all the physics that describe waves, vocal, like me talking to you, ocean, okay, the waves in the ocean, every wave that we know actually make this equation. Derive me twice, respect to space, derive me twice respect to time, multiply me by some velocity. That's all. And Maxwell understands that actually electromagnetism is a wave phenomena. So this class, actually we're going to take a pause from electromagnetism and we're going to try to summarize all the important concept of wave in one class, one topics. And next class we're going to come back and talk about the phenomena of electromagnetism as a wave. Gotcha? Got it? So I have a wonderful camera with me. I have a wonderful example for wave phenomena, which is my guitar. Okay? So the question is going to be about my guitar. So I'm going to draw a guitar right here. So this is the guitar. So hop, 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 and we're just gonna deal with one string, okay? One string, but of course all the strings obey the same physics. So today my goal is that you would understand the physics of a guitar, okay? Perfect. So the guitar length, the string of the guitar, equal to 0.85 meters. The weight of the string is really light, is just 0.03 kilograms. Right? And that's all we need to know. And I want you to notice something. When I have the guitar, here the string is actually attached to it. The string cannot move at this point. It's fixed. And also, at this point, there's a tension that pull it in that rotation. It cannot move. So this is actually the length of the string. These points are actually fixed. Okay? These points, in a professional language, called nodes. Okay? Notes. They cannot move notes. There. Okay? Good. So the first question I want to ask you, what are the different manners, okay, in more professional word, what are the different modes that the string can move? Okay? So A would be, what are the different modes that the string can move, right? So how it's going to look like. So the most easiest thing that I can think about it, okay, Ron, you said that these are the notes, they are fixed, so it's going to do this. Makes sense, right? So in this case, the string would do that, it would do that, and then it would do that. You see this point? This is the point that's gonna move the most, right? This is a really important point. It's called antinode. And this one here, node. Gotcha? Important things to remember. Great. Let's challenge this idea. Okay, so the string can move in that direction. We said that we have two fixed points that cannot move, so we can add another point in the middle and say that the string is doing that. Right? Makes sense, it can do that. So if I'm gonna add this point is actually locked in space, it's not really locked in space, but it's gonna describe the movement, it's gonna look like this. Hop, hop. And after half time, it's gonna do that and that, right? And now I want to teach you another thing which called the wavelength. Wavelength. This thing is called wavelength. And the concept of wavelength is what is the distance, if this is a wave, right? This looks like a wave. What is the distance that I got to the same location again? This is called the wavelength, okay? It's a distance that, again, in the same position. This is also the wavelength, right? So if I'm going to look at this phenomena, what is the wavelength of number 2 that we talked about? What is it?
Half L.
This is exactly half L. So lambda of case 2, right, is actually not half L, it's L. It's completely L. Why? Because I start going up, and here again I'm going up. So this is exactly L, right? And what is case number 1? Case number 1 was? Now you're correct, exactly. So I did it, but the next one is actually in the other side. We need 2 guitars to actually see it, right? And let's talk about the third one. I have another color? No, so we're gonna do it black. So the second one is me have 4 fixed point. 1, 2, 3, 4, right? And I'm gonna do that. Fit, 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 right? So this one is actually gonna be 3. And right now it's, what is the wavelength of the black? Yeah, it's a little bit too much things on the board, right? So it's a black. This is 2/3 of L, right? So it's 2/3 of L. And now you're gonna see why it's so important to have this term, which is called the antinode, okay? So the antinode, we do it with the N, because remember, antinode is the displacement of the string that moves the most, okay? Is the maximum and minima of the string, right? So if I'm gonna want to generalize all the possibilities of the modes that I can visual to see it, actually, it's gonna be lambda equal to 2L divided by N. You see it? This is hold for everyone. For 1 is this. For 2 is L. For 3 is 2 to the 3rd, and so on and so on. And I put a cool video here on the TV. You can see it. So this is a guy that put the camera inside his guitar. And it's look like this. So here there's many modes that are actually playing simultaneously, and you can see them. It's really hard for our eyes to see it. Okay, let's stop it. And I want you to, right now, I also brought this concept. I brought a huge string. Here it is. So I think this is the biggest guitar string in the world, okay? So right now, I'm gonna try to do, so like this. You see me on the camera? Good, yeah? So I'm gonna try to do the first mode so you can see it, okay? So this is the first mode, right? Now I'm gonna try to do another mode. Let's try. Oh, okay. Wait, slowly, slowly, slowly. Okay, it's like a tiger. Okay, so, oh, this is the second one. You see it? There's actually like a point in the middle that stands still. You see it? Let's do another one, harder one. Wait. Okay. Okay, chill. Okay. You see there's like, huh? Applause, guys. It's really hard. Okay. So you see that we had a sense of illusion, like there's a point that fixed in place, right? It's not moving, like standing still. So the phenomena of when you have fixed places, it's called standing waves, okay? That's the idea, and this, what we're going to do today is only standing waves, a phenomena of waves that apply also to electromagnetism, okay? Cool. So we understand what is the wavelength, okay? We kill my guitar, right? We cannot understand anything, and now I want to ask you a real question about music, okay? So the second part would be, what are the frequencies that the string can play? Okay? What are the frequencies? Frequencies is actually notes. Okay? It's a musical note. Okay? So there's a really important equation that I want you to know. You know this equation? Is x equal vt? It's a propagation motion. It's what's happened in location, velocity, and time. So we have a parallel idea in waves, which is this formula. We're gonna divide it by t, 1 over t, multiply by v. This is the distance that the wave actually did. This is the frequency, 1 over time, the tempo, how much time it takes to make it. And this is the velocity of the wave. So this is one of the two wave equations, okay? So what is actually wave? Wave is energy. Is energy that propagates in some medium. That's the concept. So right now when I pluck the guitar, I actually enter a lot of tension into the string, and right now it's stuck inside the string and do this motion. So it's move at that velocity, have this manner, this is how it look like, and this is what it sounds like. What is the tempo of it, okay? How fast it's oscillate. Okay, good. So we know lambda, right? We already understand that. So if you want the frequencies, we can say, okay, it's just v divided by lambda. And lambda we know it, it's L, V, right? Here it is. N goes up, and here we have 2L, right? This is all the frequencies, and we see that the frequencies actually depend on which mode I am. You see it? And I want you to see this. Who is that frequency? It's the first frequency, okay? And it's really important. Usually in musical instrument, this one is so dominant, okay? So usually we call this the fundamental frequency, okay? And all the other frequencies are just multiplication of this frequency, okay? Got it? Perfect. So I want you to remember this formula, it's really important. V2L, and this is F1, right? So we have that, good. And now let's do a more physical problem, right? I'm going that direction, good. So another thing about the thing on the guitar, so I want you to see that actually guitar player, if I'm gonna change the length, what's gonna happen to the frequency? Change, right? So all the concept of guitar players is actually to change the length. This length, this frequency, right? And if I'm gonna press here, what's happened to the string? What is the length right now? This is fixed. It cannot move from here to here. You see? And that's the concept. When I play the guitar, like, I simultaneously change a lot of notes, a lot of lengths. While I'm singing, I'm changing the length of the string, right? This is the concept, okay? Another thing that I can do to change it, I can change the tension of the string, and that's what we're going to do right now. See? I can change that, and that's the reason I have these keys, right? I can change it. I don't want to do it because I really love this sound, okay? Okay, so this is the concept, and guitar players have this thing. Hey, I want to sound a little bit higher. So let's short all the guitar. And now, the same melody I played before just shifted, okay? All the guitar is short, okay? So this is the concept when playing guitar. So let's talk about this phenomena of tension. So here, C, okay? So the next question, okay, it's gonna be that I play the guitar, okay, and I put the frequency F1 to be the note A. The note A is 110 hertz, okay? And I want to know what is the tension, what is the tension in the string. Okay, so we are looking for T, and I put T node, not to be confused with time, right? The time period. Yes, and I'm going to tell you that in some tension, actually the string can, what can happen to the string in a really high tension? Rep, exactly. So this is going to call it Px, which is the dangerous one, and this is 2000 newtons. Okay, this is going to break the string. Perfect. So, okay, so I have the frequency, and we already learned a formula about the frequencies. So F in general equal N multiplied by the fundamental frequency. They told me that we're going to play 1. So this is 1, this is V, this is 2L, and this is 110, right? And now I want to give you a formula about velocity in a string. So the velocity in a string of the disturbance is known. We can extract it by this formula. It's the root square of the tension in the string divided by mu. And mu is the mass density, okay? And usually, and you know already density, you know they have volume density, we have the area density, and we have a line density. Which one would make sense according to the geometry of a string to be here? The line. So mu is actually the mass divided by the length. Okay? That's all. If it's uniform. I never saw a question when it's not uniform. Okay? So in exams. So I think we are cool here. So if I want actually to solve the question, to see what is the tension in the string, I just need to apply that here. So let's do it. So if I'm going to put this inside, I'm going to get, only as a parameters, yes, I'm going to get the T0 equal 4 F squared multiplied by L multiplied by M. We know everything. We know this is to be 110. This is given almost a meter, right? And this weight of the string is also known. And this result is 1, 2, 3, and 4. Beautiful result. Would the string break apart? No, because it's smaller than this tension, right? And actually, who is really care about that? This is the frequency of the fifth string of the guitar. Okay, the fifth one from the bottom. This is, okay? And usually, just to tell you, because I think it's interesting, when we play instruments, musical instruments, and I plot the frequency and the amplitude, how strong it is, you're going to see this pattern. You're going to see significance frequency, another significance, another significance, another significance. And this is the ID of the the instrument that you play. This can be F1, this would be F2, and this is going to be F3.
What's the y-axis?
Y-axis is the amplitude, how strong the instrument actually play. So that's what's going to happen when you're going to check the frequencies of the instruments. And if you're going to look at drums, like this, you're just not going to see any interesting frequency. Okay? This is not musical, and this is a musical tool. And if the height would be different, for example, this would end here, and this would be really high, so this would be something else, not a guitar, maybe harp, maybe violin, maybe trump, right? So this is the concept. Okay, next question. The next question is, what is the human range of frequency? Human range frequency. Do you know it?
20 hertz to...
Nice, nice. Okay, so let's do it here. So the human range, we cannot hear all frequencies. Okay, we can start, usually the lowest is 20 hertz and the max is 20 kilohertz. Let's do the zeros to be more dramatic, right? And you know that below 20 hertz it's really hard to hear it, but elephants can do it. Elephant, whoopa. So elephant actually can hear even 14 hertz, which is insane. And this is called infrasound. They can hear below what we hear. And dogs can hear crazy world. They can hear 6,000 hertz. Okay? It's 3 more than us. They have a zoo of sounds that we cannot hear, right? And this is called ultra sound, right? And today you actually cannot hear 20 anymore. You know why? Because you are old. Because you went to a lot of Yom. You fucked up your ears, right? So right now I have here an exam that I put on the string. Right now it's playing these sounds. And I want you to let me know, you know what, let's turn on the volume really high. So this is the strongest, okay. You can do more, great. So right now, I play this sound, okay? And I want you to let me know when you can hear something. Okay, the more interesting part going here, I think. Now you hear it, right? So everybody that hear it, please pull the hands up. You hear it? Don't be shy, okay? And now we can understand how old each one of you in terms of frequencies, okay? It's not really like everyone is dependent, you know, it's not like a really way to know your age, but it's a way to know how much you fucked up your ears till now, okay? So a party boy would be like crazy, and I think you don't hear all the lecture. Okay, so cool. So everybody's here, it's really low. It's gonna be, let's take it to be, yes, and I'm gonna take it to the interesting part. Okay, I still hear it, and in some point I'm gonna lose it, okay? Okay, I still hear it. Everybody still here. Good. Good, you're a really good kid. Wait. I think, no, I still hear it. Good, I'm not that old, okay? Good, okay, 3,000. I lost it. I lost it at the 14,015, okay? So now you know how old are you, okay? Good. So let's move on. This was some introduction to the next question. And the next question is, what is the highest note you can hear from the guitar? Let's say you are a really good boy, okay? Let's say that you got this, okay? We saw not, okay? I think most of us lose it around here, right? Somebody else still could hear? Yeah, you could hear? Nice, okay? Let's go here. Okay, so the next question to you is, what is the highest frequency? What is the highest frequency that we can hear from the string? So we know that we need to understand actually this is F higher, why? Right? And this is equal to N, the mode that we are talking about, multiplied by the fundamental frequency of the string, right? So the fundamental frequency, we chose this string, right? We chose this. This is the frequency we are talking about, right? So this is fundamental, I know it to be 110. And this one, we just said, we want to see what is the highest frequency we can hear. So this is gonna be, and now we need to find this N. And this N turned out to be 1.1018. And this is a valid result. What is N? N is the number of the antinodes, right? Be careful, okay? Nodes is the point that move the most. Antinode, sorry, is the point that move the most. And nodes is actually, I'm not moving, okay? This is the nodes, okay? So we actually cannot hear 182, right? Because we're going to exceed that. So our real result is 81, right? And this is going to give us the frequency, which is 19,910 hertz. Okay, like this is the highest thing we can hear from the string, right? Perfect. How this wave look like? How the string need to actually oscillate so we can see it. It's another way to ask what is the, I delete it, but what is the wavelength, the one that correspond to it. So how I can find the wavelength? I know n, and I know the equation for wavelength. It's just 2L, right? It must have the same units, meter, divided by n. So 2 multiplied by 85, the length of the string, divided by 181 is equal to 0.009 meters, which is approximately 1 centimeter. So how the string gonna look like? It's gonna look like this. Every 1 centimeter, we're gonna have this thing, curve, right? So it's gonna look like this, and of course, maybe it's gonna be shrinks, right? I just want to emphasize the amplitude, right? It can be smaller, right? So this is how the string gonna look like. And now I want to tell you something. You know that we actually played on the guitar. The propagation was locked inside the string, trying to move it, to change its geometry, right? Play with the tension. But it's not here. It's there on the guitar. So what needs to happen for the propagation, this wave, to actually come to our ear? It needs to go to some other medium. The medium of the string need to get, the propagation in the string need to get outside of the string, go to the medium which call air, and come to my ear, right? That's what needs to happen. And I really want to talk about something really important, which we have two kinds of wave, two kinds of propagation, of disturbance, right? So one of them is the one that you know, that if I'm gonna take the string, right? So I'm gonna do the disturbance in this plane, right? And it's gonna move it that way, right? Disturbance that way or that way, right? And it's gonna move that way. You see it? The string went up like waves in the ocean. But when it's come to air, and this one called longitudinal, longitudinal wave propagation. But in air, something else is happening. The propagation coming, right? So what's happened? There is like a punch. The string actually moved and slapped to the air. That's what actually the string is doing. It's slapping to the air, and this thing needs to go in the same direction the propagation is going, right? So I brought this demonstration, okay? So you can think about those as the air molecules, okay? So when the guitar gonna give it a punch, that's a strong punch, you see what's going on? That's how it looks like. Actually, your ear actually sensitive to changing in pressure of air molecules. If the molecules are dense, it means, whoa, something happened, I heard it, something happened. If it's loose, nothing happened, okay? So that's what the guitar is actually doing. So when I plug the guitar, that's what happened to your ear. Understood? So, but we need to understand how we can shift the knowledge that we have on the string into the language in the air, right? So that's what we're going to do here. Sorry, guitar. So, okay, so we have the same equation. Okay, we have the basic equation of propagation of disturbance, V equal lambda F, right? So what is going to be the speed of the propagation in air? Maybe you heard this term before. Speed of sounds, exactly. And this is really fast. Speed of sound, and it really depends where you actually, which medium you're going to do it. Because if there was a train and you put your ear on the rail of the train, you're going to hear a different speed. It's the speed inside this metal, right? But in air, it's the speed of sound in air. And in different gases, the speed is different, right? Okay, so this is equal to, it's important to know this property, meter per second. If somebody going to shout at me, okay, say something, and I'm going to run this first, I'm not going to hear it. I'm going to be faster than the disturbance of the spring that you saw. I'm going to be faster than that. And we can do it. Airplanes can do it. Can break the speed of sound, right? Good. So another thing that we know, what this is going to be. What's going to be the frequency? If I'm going to play this thing, the frequency. Okay, let's make it clear, okay? So if I'm going to punch somebody, give it a set. What is the rate that it's going to feel the pain? The same rate. So what's actually the guitar doing? So the guitar is being played and it's punching the air. So the frequency gonna be the same. So no matter if I change medium, the frequency gonna be the same. If I'm gonna be at the pool and I'm gonna slap, okay, the water, the frequency, the bubbles that you're gonna see underneath the water, the propagation of water, condensed water, gonna be at the same rate I'm gonna punch it. If I'm gonna talk to you and you're gonna be underwater, the frequency gonna be the same. This is clear? So this is actually the same. Okay, so how we can say frequency is conserved when moving through mediums, right?
Depending on the medium.
Not depending on the medium. No. But if this is a given thing, this is a physical property, chemical bond, how much it gives the propagation to move, this is not changing, right? Not changing, which means it's equal to what we found before, 1 to 1 multiplied by the fundamental, right? This was n, this was the fundamental, right? So who is going to change?